The singularity is a bit of space-time that preserves all the information of objects that fall inside the black holes. The singularity is a bit of space-time. As we said, for numbers, we said also numbers are the bits of space-time. That's why the singularity is a number or information. So here you have a hint how we could maybe in the future explain the holographic principle. Holographic principle says that there's information on top of the black hole. But here we are talking also of information at the singularity. So the singular numerical relativity is going to explain how the information from the singularity is related to the information on the surface of the black hole. That's very beautiful. Good morning, good afternoon, good evening. It depends on the time you are watching this video on our new channel, the Lutia channel. Here today we are launching a very important program, and the program is all about the study of a new theory of physics that is going to revolutionize physics. Therefore, we are talking about the great revolution of modern physics. We say this because all those who have been studying physics, they know exactly what is expected in physics. So my name is Jacques Lutia from the Democratic Republic of Congo. I am calling for the attention of all the leaders. You may be a political leader, a religious leader, or a scientist, a business leader. You have to understand this. It is so important. Therefore, I expect that you will be the first to learn. You will be the first to listen and finally attend to this great revolution. Great revolutions have been taking place in history. Particularly in science, we had a very big revolution 400 years ago. And in science, revolution is needed mostly when we are looking for a solution to some problems, because science is all about explaining our environment, explaining how the universe works, explaining about ourselves as human beings, how we connect with the rest of the creation. That's what science is all about. But there will be a time always when we are stuck in wrong ideas and we can't make any progress anymore. So what I'm trying to say here, that when we have wrong ideas, of course, we can not progress at all. And this is what happened in the past. In the past, we had such a problem. I would like to show you this table of evolution of science. It shows clearly here that we wasted a lot of time 2 million years before Christ. Of course, this number is just an estimation, but the reality, it must be longer than that. So we spent a long period of ignorance where we didn't make any progress until this point you see here. Of course, here it shows the 18th century, but in reality, the revolution began earlier than that. It began in the 16th century. What happened here? Here, we were able to understand the position of the Earth in the universe. Copernicus was a scientist who lived in the 16th century and who came up with the idea that truly the Earth was not the center of the universe. It was an idea that was entertained by everybody, and to the point that Copernicus will pay a heavy price for just having said and having found that the Earth was not the center of the universe. Instead, it is just a planet that is orbiting our sun together with other planets. Then Copernicus, of course, died. But 60 years later, Galileo appeared. And Galileo made a telescope. He wanted to see exactly what happens in the skies. And he was able to find out that there are many other planets out there, many other stars which are being orbited by other celestial bodies. And especially here, his focus was on Jupiter. He was able to see that Jupiter has moons, and those moons are orbiting Jupiter. So he concluded that the findings of Copernicus was right. Then starting there, you see, from that time, starting with Galileo, we will begin to study motion. And the study of motion is relativity. It means the study of relativity started at that time. And the most important thing that Galileo did, he was able to measure the speed of objects in the free fall. Standing on top of the Tower of Pisa, Galileo was able to conclude that all things fall at the same rate if we remove the air and other obstacles. So even the feather of a bird can fall at the same rate with a stone. The stone is so heavy, but they can fall together at the same rate. And then he measured the speed of the object in the free fall. Measuring the speed of the object in the free fall was measuring gravity. Now this is something that I am revealing to you, if you didn't realize it, that Galileo measured gravity. He was the first to measure gravity. Even though just after him will come Newton, who began to study gravity as such, and he developed the theory of gravity, giving us the formulas and everything, how it works. Even so, Galileo should be recognized as the man who measured gravity for the first time. This is true, and it will be actually the focus on our studies here. Because of what Galileo did, then we can solve problems of physics. So at that point, you see that starting with Galileo, the father of science, we moved to Newton, the father of modern physics. Then it continued up to Einstein. When Einstein came, almost 250 years later, after Newton, then Einstein put all these studies together and made what we call general relativity. He modified, of course, some of the theories that were already accepted, coming from either Galileo or Newton and others. He modified that, and he gave us finally a branch of studies of physics which focuses only on the motion of big objects in space. In the meantime, as you see here, we went from transformation of material, then from the time what we understood our position in the universe, we began the study of energy. It means the transformation of energy. People started digging inside matter to understand what is inside, because they found out that it seems matter could really produce energy, could help us to produce energy. And then, therefore, we began to transform energy. Anyway, we went through all this stage. This is not my focus on this. I want to just show you that in this period of time, we discovered the world or the universe inside matter. And there we found the world of atoms and particles, which became again another branch of physics, because to explain what goes on in the atomic world, how the particles behave, we had to find another theory that is fitted to the behavior of particles. And that's what we call quantum mechanics or quantum physics. These two branches, so on one hand, Einstein with his general relativity, and the other hand, we have other physicists with the quantum mechanics. We have performed so well, mostly during the past century, the 20th century. It is called the century of light, because many things were done during the 20th century. Then, by the 70s, in 1970s, we entered a new era, the era of transforming information. So the two theories, general relativity and quantum mechanics, led us to this point where now we understand things in terms of information. And today we live in the digital age. It means these two have been doing well. Quantum mechanics and general relativity have done a good job, but there is a problem because they do not agree together. It means you cannot mix the formulations. The worst of the thing is that both cannot explain gravity at the fundamental level. Therefore, it became really a problem for physicists. Fortunately, general relativity predicted that there's a place where these two studies can meet, where it's inside black holes. Black holes are these huge excavations inside space-time or in space. They are now, today, they are considered as objects of studies. Therefore, scientists have been studying the black holes, trying to make a theory of a theory that will explain the gravity at the fundamental level. So this research has been going on for a long time, but there is still a problem until today. The solution has not been found. What went wrong? Were they looking for the solution at the wrong place? I don't think so. The place is right. The black holes are the right place for us to find the solution. Black holes, as you see them, at the center of the black hole, there is a singularity. Then here, to study what goes on here, physicists have been using a particle in order to understand what goes on inside the black hole. But it did not work. Many theories have been put forward to explain how particles behave in the presence of gravity. So, and the search continues until today. So what to do? Why we did not find the solution here? Because particles are not compatible with the singularity. The singularity is the only thing that exists inside the black hole. And whenever an object falls inside the black hole, it will be destroyed, completely absorbed at the singularity. Crushed, as they say. The object will be crushed at the singularity. Therefore, even light can't go out. I know that many other theories that have been made regarding this matter, trying to use particles, to force the particles to exist inside the black hole by saying that a particle goes in, another goes out. That was simply a speculation. The fundamental idea, or the basic idea that we had about the black holes, that the black holes absorb everything. And even light can't go out. It means nothing can get out of the black holes. That's the fundamental idea. So now, the point is how we can solve this problem. So I am here. I am the problem solver. I know what is compatible with the singularity. I discovered that there is a way to find a tool that will be compatible with the singularity. And through that tool, we can explain quantum gravity inside the black holes. So, I came up with a new theory we call the Singular Numerical Relativity. I have been working on this theory for 9 years, and I have made a lot of progress solving many mysteries of physics. That's why we are talking about the Great Revolution. The things I'm going to reveal to you are very difficult sometimes to digest, but don't be judgmental. Simply study and try to understand. Just try to connect to what the universe says, not what you think. That's really my advice. So here, with the singular numerical relativity, we will be able to resolve all the issues regarding quantum mechanics and general relativity. So let's understand today what is this title about. What is this name that has been given to the theory about? And that's all we are going to do today, is just to explain this. In this video, we will just explain these three words. What is the meaning? And we are going to give you, in the end, the mission of what exactly the theory is going to do. So let's begin with understanding about these terms. Of course, singular comes from singularity, numerical, number. Relativity is what we call flexibility. Flexibility of space, flexibility of time, flexibility of space-time. I make it very clear so that there is no confusion here, because time, space, and space-time are three things, very different things. So the first word that we need to understand is about relativity. What is the meaning of relativity? For you to understand relativity, of course, you have to base on what exists already, because we have already very beautiful explanation of relativity. However, today we are going to insist on the essence in physics, what the word relativity means. As a theory, we know that relativity is the study of space, time, and gravity. It's clear. And it says that space is flexible, time is flexible, and in the presence of objects with mass, space combined with time band together. They make, of course, a fabric we call space-time, and that fabric bends. That's correct as a definition of the theory. But I have said we need to understand the word itself as we should understand it in physics. So what relativity means? I want to show you this. This is a coil spring. This coil spring can do this. You see, it takes many shapes, different shapes, and can bend. So this is what we call relativity in curved line. Relativity in curved line. But at the same time, we use the same spring and we do this. It's very hard. Huh? We stretch and contract. Stretch and contract. Here we see that it is not bending. This is happening in straight lines. So what is the difference between the two? Should we say that we have two kinds of relativity? No. We don't have two kinds of relativity. We have only one relativity. But now we need to understand what exactly happens. Because here we see curved line, and here we see straight line. So what happens? Einstein explained very well here that space and time make a fabric we call space-time, and that has 4 dimensions: 3 dimensions of space and 1 dimension of time. These dimensions interact and they give us the curved line in the presence of objects with mass. So here, mass is the key. Mass will interfere. I will show you this. Basically, as you see here, Einstein started explaining first the relativity of time. This was his very the very start of the explanation of relativity. It was about the relativity of time. And Einstein explained that time dilates. So it means time can become longer or shorter, longer or shorter. So time here doesn't bend. Space at the same time also can become, can contract and stretch, contract and stretch. Therefore also space as such doesn't bend. Do you get the point? Even though space has 3 dimensions like this, what happens to the 3 dimensions of space? When they interact with time, these 3 dimensions are doing the same thing. This one will do like that, stretch and contract. Here also it will do the same, stretch and contract. Here, same. So the XYZ of space interact with the 1 dimension of time the same way. Therefore, that's what happens basically about relativity. So relativity is all about this adjustment of dimensions, the adjustment of dimensions. So when these are working, then when we go to the places where we have objects with mass, now space-time of course will be curved. Why? Because this dimension each interacting with the dimension of time will adjust to a certain, to its size, depends. So here, this may be like a little bit longer, or the other one will be shorter, and so depends on the position of the object that is pressing down the space, or space-time, I mean. So that's what happens. But basically, all here or there, in straight line or in curved line, space-time do the the same. They interact the same way. Therefore now, to study space-time geometry in straight lines, we don't need the 3 dimensions of space. We need only 1 dimension. Why? Because what happens here and happens there. Do you understand? So we are going to study space-time in just 2 dimensions. So the interaction between space and time, 1 dimension space and 1 dimension time. That's what we are going to do here, and that will be our business. Because here already Einstein explained, and Einstein was able to demonstrate how gravity works in curved line. But when it came to this area here, Einstein failed to explain gravity in straight lines. He failed at that point. Why? Because simply he followed the wrong advice of his colleagues. Einstein was misled at this point. He understood everything. He understood everything. What I have said here, Einstein knew all of that. And I think many of you understand also somehow. But the point is, he received the advice to develop the theory of special relativity using the 4-dimension space-time. That was already wrong. The second point is he was told that this is only appropriate for objects moving in straight line and at a constant speed. That's very, very misleading, because this straight line that I am showing you here that happens in every dimension is dictated by a natural law. There is a natural law that dictates here how space and time should interact in these 3 dimensions and 1-dimension time. Do you understand? The natural law that exists here must be obeyed. There is no escape. And that's what Einstein missed also. He could have insisted on that, but he did not understand. So that's why we are going to resolve the problem. So now you understand that what happens in the straight line is the cause, and what happens here is the effect. The effect just because the intervention of mass, the interference of mass, objects with mass, give the curved line. But generally, when time and space interact, they interact in straight line. That's why if you go in the universe, you will have places where you will have such a description. So inside galaxies, this is what Einstein explained. Big objects, for example, our sun with all the planets around it, they all move together following this 4-dimension curved line description. But in the regions where we have no particles with mass, then in those regions we don't have a curved line. So outside the galaxies, I will give you more explanation about this because there is a chapter where we will insist on exactly what happens in the regions outside the galaxies, because the galaxies are these areas or these regions of space where particles with mass gather. But out of the outside the galaxies, there is no, the objects there may have or not have mass, but in majority they don't have mass. In majority. I cannot tell exactly what happens there, but at least we do understand that the objects, all the objects with mass gather around the galaxies. So outside the galaxies, it must be something different. That's why I'm explaining that way. So now we do understand that relativity is about adjustment of dimensions. When something adjusts, of course, it's variable. It means it gives us many possibilities. As you see here, you can do this. You can adjust to any size you want. So this is many possibilities we have. Many possibilities, many outcomes, many options, and many degrees of freedom. So the degrees of freedom that we see in the quantum world happens even in general in the universe. And that's what gives birth to what we call diversity. Diversity that we see in the creation is part of, or is the work of relativity. So now you understand what relativity stands about. It's about adjustment of dimensions. Let's go to the next point, which is understanding the word numerical. But I put them together, numerical relativity, because you are familiar with this numerical relativity that you are using in physics. In physics, you have numerical relativity, which means the study of the formulation of general relativity. So it's a mathematical study of the formulation of general relativity. I don't know why that name was given. But anyway, let's talk about first the number. Because we are insisting on this word, number. What is a number? A number is very mysterious. It's the most difficult thing to understand. What number is all about? Scientists in the past 20 years, they have been asking so many questions about this, because they are wondering why numbers are really working, because we live in this age, the digital age, and we see that with numbers we perform miracles. What is happening in our information technologies? We see that it is truly a miracle. How is it that numbers can give us such results? Everything we do in life, we need number. Why? It's because numbers are part of the creation. Numbers are the building blocks of the fabric of space-time. The fabric we call space-time is made of numbers. So numbers are not the signs. The signs can be produced in Japan, in Korea, in China, in Thailand, in Russia. They have their own alphabet, no? Also, and you can see that in the Arabic world, they have their own way of writing. The Western, they have their own way. And we see others. They have their own ways of writing. But when you call people from all those different places I have cited here, and you show them this, how many I have here? Everyone will say in his own language, oh, you have 3. Why? Even though they come from different places, but everyone will have the same perception of this. It means numbers are inscribed inside our brains. We deal with numbers in communicating with the rest of the creation, communicating with our environment. Numbers are the one that help us to do so, because numbers are real. They are part of the creation. Unfortunately, you cannot see them. You cannot touch them. And they are working on another level, a level where it's very difficult for us to understand the invisible physical world. So we have the visible, but we have also the invisible physical world. The invisible physical world, I'm not talking about the spirit world, okay? I'm talking about the invisible physical world, where we have dark matter, dark energy, that area where we talk about black holes. In that level, it is where numbers work, numbers operate. Do you understand that? So numbers are real. Numbers are not the signs that we write. So you have to understand from now on that you deal with numbers in order to do everything. Even animals use numbers. So it's not a matter of going to school to learn 1 + 1. No. It's a matter of really living life itself. Even our grandmothers who didn't go to school, they used numbers. You see? So it means numbers work, not because we invent them, no, but because numbers exist as a part of the creation, as the bits of space-time. So space-time is made of numbers. That's why space and time are flexible, and numbers that make them must be also flexible. And here we talk about numerical relativity. The numerical relativity we are talking about here, it means numbers are flexible. It's flexible. It means flexibility of numbers. Numbers are relative. And that's what we are going to learn in our first chapter. So please try to understand this. I will explain all of this in the first chapter, how I came about with this idea of numbers and what happened to the numbers. You will understand exactly what numbers do and what numbers are. So the next point is about the word singular. As I have said, that for me, the understanding I have about numerical relativity is that number is relative. Number is relative. That's what the meaning of relativity or numerical relativity. But I encountered this established name of used in general relativity. I don't know who gave the name, so I could not oppose anybody in that sense. All I did, I use my skills as a man of relativity, understanding that a name can have many meanings. So that's talking about relativity. Many meanings, many possibilities, many choices. So I can't insist on my own idea. Then I had to add this word here, singular, and became singular numerical relativity. Why singular? Singular, as we have learned already, that singular comes from singularity. The singularity is that small object at the center of the black holes that crushes everything that goes inside the black hole. And I say that the scientists have been trying to explain this using particles, but particles are not compatible with the singularity. So what is the singularity? And here I am revealing to you that the singularity is a number. The singularity is a number. So what happens? When an object falls inside the black hole, it goes straight to the singularity where it is crushed. Crushed means as if you click on your camera trying to take a picture to capture the image of a certain object. So when you click, that's what crash means inside the black hole. An object is crushed by the singularity. Of course, the object will disappear. But all the information from that object will be preserved by the singularity. The singularity will register all the information of the content of the object. That's why the object that goes inside the black hole must be melted away, completely vanish, so that you will get all the details about the object and serve it as one number. So the singularity is a number. So if you want to go to the black holes, you visit a black hole, you must be a number. Don't go there wearing your suit. You will be crushed. You have to go there as a number. Then you will be welcomed by Mother Singularity, because the queen of all numbers is singularity. So here we do understand that the singularity is a bit of space-time that preserves all the information of objects that fall inside the black holes. The singularity is a bit of space-time. As we said for numbers, we said also numbers are the bits of space-time. That's why the singularity is a number or information. So here you have a hint how we could maybe in the future explain the holographic principle. Holographic principle says that there's information on top of the black hole. But here we are talking also of information at the singularity. So the singular numerical relativity is going to explain how the information from the singularity is related to the information on the surface of the black hole. That's very beautiful. So at this point, we can go to the last point, which is talking about the mission of the singular numerical relativity. What the singular numerical relativity is going to do. First, we are going to complete general relativity, because general relativity, as I said, was left incomplete by Einstein. Einstein said, I can't understand. He tried up to the last minute of his life, laying down in the bed in the hospital, still trying to write something regarding this matter, but he could not make it. Then now we are going to complete what he left unfinished. And here, to do that, we just need to explain the interaction between space and time in straight lines, describing gravity. Okay? We can explain gravity in straight lines. There's no problem with that, because the law is the law of nature. It's not something mysterious, no. But only Einstein forgot. I have the full story to tell you in the future about Einstein. So when we study space-time in 2 dimensions, we will be able to granulate space-time, to quantize space-time. And we are going to make a ruler so that we can measure space-time. Space-time has a ruler that we can use. A ruler, just the ruler you are using to trace your things on papers, you know. There is a ruler of space-time that you can use to measure how big here, what is the height, what is the length, you can do that with a ruler of space-time. Then the second point is to resolve all the confusions, ambiguities regarding general relativity and quantum mechanics. General relativity and quantum mechanics have been living in conflict somehow. But there is a point where they unite, is not to explain quantum gravity. Not to explain gravity at the fundamental level. Everything is okay. They can talk each one in his own language. So they don't mix anything. But they agree not to solve the problem. That's why we are here to help, to bring them together. And we have told you already about relativity, about general relativity. That general relativity, where we are going to just study the interaction between space and time in 2 dimensions. 1 dimension space, 1 dimension time. What about here with quantum mechanics, what we are going to do? Quantum mechanics is formulated based on the double slit experiment. It is so beautifully explained by Young. When you see the graphics that Young made regarding this, it's so beautiful to understand what goes in here with the wave and the wave function. It's so beautiful. That's perfect. Nothing to change. However, we got this branching. The branching we could call branching of the many worlds. But I'm not talking about the many worlds as many worlds interpretation. It's not exactly that what I'm trying to say. This branching is used in your computers. In our computers, we have this. I remember myself, for the first time when I bought my computer, it was 16 megabytes. Compared to the computers we have today, that's very small. 16 megabytes of memory. Oh my God. Why? Because of this. 1, 2, 4, 8, 16, 32, 64. So those are the numbers that we use in our information technology, in our computers, cell phones. This is what works inside. Then scientists are not happy with this. They are trying to now, they have been working already on what we call quantum computers because they want to change this. But I think they have a problem how to really produce what we call quantum bits in large symmetry group. They don't maybe achieve yet that. They have made some progress. That's no problem. But we need to follow what nature says, not what we are trying to make by our own. Nature has a very automatic way of giving us a branching here which will be truly compatible with what the double slit experiment demonstrates. The double slit experiment is showing, you see here, the interference pattern is with many stripes. Many stripes. But here you see what happens. You go from 1, 2 only. And if you go deep, when we are going to discuss about this, you will understand that even here, actually it doesn't work as 4. It is still 2. Even here it will still be 2, 2, 2, 2. And that's but considering what they believe to be true, the numbers look right, having 1, 2, 4, 8, 16, 32, etc. It seems to be right, but it's not yet what we want. We need a system better than that, the quantum system that corresponds to this graphic shown by the double slit experiment. And it is here we are going to find quantum gravity for quantum mechanics. Do you understand? Big revelation, huh? That's a big revelation. It is here. From here we are going to explain quantum gravity. So be ready, because it will shake some hearts and heads of people. The brains will shake. I know. So at that point, we will have completed everything. Okay. What I would like to say maybe it's regarding this mission. There are many things that we will explain. We will explain the holographic principle, because to reach to the singularity, you have to pass through the surface of the black hole. And to get in, you need an explanation of the holographic principle. And there, when we meet the singularity, you must know that the singularity was at the beginning of creation. So mean we have to talk also about the Big Bang. We need to talk about the black holes. We need to talk about all the small problems that we have been experiencing in quantum mechanics, with like measurement problem, entanglement, uncertainty problem, all probabilities. We have to resolve all those matters. And this is not just something I'm saying out of nowhere. No. It is clear and the answer is coming. So just follow my explanations. I still have many videos to make, because this will take at least 20 videos for me to explain everything. Do you understand? So please follow me and you will be satisfied. Don't make comments if you don't understand. Wrong comments if you don't understand. Because you will create your own problem. You will be left behind. These mathematics will be studied even in elementary schools, because the mathematics are very simple, as I'm going to show you in the next chapter. The mathematics are very simple, and it's supposed to be given already in the elementary, but you never studied it. You became a president without studying the relativity of numbers. That's a violation. You became a scientist without understanding the relativity of numbers. That's not accepted. You became whatever, businessman, without understanding relativity. So please, for you to be better than you are today, study the relativity of numbers. The relativity of numbers is the solution to all these problems I have enumerated here. So please be with me in the next chapter, and I wish you good understanding. Thank you.